the calculator tell me something, I wrote a different thing. The QZ for the box B, point B should be 11.9483, not 11.9843, okay? And I've canceled the miss and make. And later on, before the break, I told you guys the values don't match. I find out why, because I've written this value wrongly. Okay, it's 9483. And then the values over here is exactly the same, whether you take from the top section or the bottom section, the Q is the same, okay? And then this step is the same, whether you take from the top or from the bottom. Okay, right. So this is all that I'm going to do for thin wall analysis. As I mentioned earlier, thin wall analysis is difficult. Okay, it's not straightforward. Like you can see now it's easier because I've created rules for you to apply. Without those rules, right, it's very, very confusing. Okay, and I'll post homework tomorrow so you can have more practice on these problems. I'm going to go into a new subtopic. Okay, so the new subtopic that we're going to talk about is known as longitudinal shear. And you have to apply whatever that has been taught so far. Yeah, you have to apply everything. Then, and I mean, when I say everything, you have to apply, also to apply thin wall analysis. And there's a additional 2 rule. Okay. So what do you mean by longitudinal shear analysis? So we are going to analyze the strength of joints due to shear force loading. The word I will emphasize over here, the joints. Okay, the word I'll emphasize over here is the joints. So let's look at a structure. Okay, let's look at a structure. So let's look at a okay. What you see over here now, if I were to draw the transformation, is this is our X, this is our Y, and then you have our rotation in Z. Okay. So you can see that this structure is simply supported and there's a load on the mixed span. And there's a term that you see over here, which is S. Okay. So S is the spacing of the fastener. Okay. And then the view you see over here, right? The view you see over here on the right hand side, this is the cross-sectional view. So when that's the case, I'll draw the transformation so that you can relate. So this is the Y, this is the Z. You have rotation about X. Okay. So just how this diagram relate to one another is you can see that this fastener over here belongs to the top. This fastener over here belongs to the bottom. Okay, so we can relate. So a unique feature on this case is the cross section is made up of 4 different components. Okay, so I'll show you now. So this is member number 1. This is member number 2. This is member number 3. This is member number 4. Okay, and all of them are held by fastener. Okay, so you can see over here, this is fastener number 1. This is fastener number 2. As you can see from here. Okay, right. So we have 4 members connected into a solid structure, right, by fastener. Okay, and always remember, right, so from here, so always remember failure will always occur at the joints. Okay, because the joints are the what? The joints in general are usually the weakest. Okay, so where are the joints? Okay, so I'm going to sketch in red. If failure will occur here. Failure will occur here first. Failure will occur here. Failure will occur here. The red regions are all your failure regions. Okay, so it's like our human body, right? You guys are still young, you don't feel it. But for me, where's hurting are my elbows, my knees, okay, my weakest point of my body, because they're the joints. Okay, the joints, we have a extra movement and you have wear and tear. Likewise on the structure, the joints are always the the weakest. Okay, hold on. There's
your cast in to an ADR studio, which is a recording studio, and you put the picture up on the wall.
okay, so failure will always occur at the joint. Now, the formula that we apply for this analysis, okay, the formula that we're going to apply to calculate is we're going to apply the formula Q. Okay, Q, which is again our shear flow, right? So we know that Q is equal to VQ over I. Okay, and the unit, as you can see, the unit is in Newton meter cube over meter 4, and we know that this is Newton per meter. Okay, now Q in terms of fastener, okay, in terms of fastener can be applied as in terms of fastener. So Q is equal to fastener resistance force, and you can divide this by fastener spacing. Okay, so the S over here, as you can see, right, the S over here represent the fastener spacing. Okay, it represents our fasteners spacing. Right, and if you look at the units, fastener resistance force is in Newton, and this is also in what? Meters. Okay, so Q over here, we still satisfy Newton per meter. So how does this actually, what, like, we would like to ask, what is fastener resistance force? Right? We like to ask what is fastener resistance force. So if we were to look into this cross-sectional view again, right? If we were to look at this, so the fastener resistance force is, I'm going to draw this, okay? This is, you are going to pull out the fastener. So this is our fastener resistance force. Okay, so how now the question is how the fastener, right? Or why, not how, this is where it can be really, or why the fastener resistance force is related to shear flow, right? We usually ask ourselves, how does this work, right? Because if you look at from this point of view, if you see how the fastener resistance force is applied, you realize that it's 90 degrees from the what? From the surface. Yes or no? Right? It's 90 degrees from the surface. But if I were to magnify this point, right? If we were to look into this section now, right? So if we were to look into this section, so if this is our, I'm going to draw part of it, okay? So this is our fastener. Okay, so I'm going to draw a circle first. Let me sketch out a circle first. Okay, and then this is our this part I'm drawing. Probably too much of it. All right. So this part I'm drawing now is the fastener. Right. So this is the fastener. And this is the wood. Yeah, so this is the member. Right? So when the force is applied, so the force, fastener's force, so let me, this is obstructing. I did not plan to draw this. So this is our fastener. Right? So the force we apply is in this direction. This is the fastener resistance force. And in order for the fastener to move, if we look at the surface, right, it has to move, okay? The fastener will move in this direction. And this direction, as I've drawn, or the opposite, okay? So the resistance should be opposite, okay? Because the fastener is going towards the right, the resistance should be going towards the left. This is the resistance, right? So we know that the resistance is in this direction now, from there. So if we were to draw an element, okay, if we were to draw an element now, element should never be a cube. I do apologize. If we were to draw an element now, right? So now, what we see on the plot, what in this in this red arrow over here, the relative is this over here. Okay, and then the shear flow is coming down in this direction. And that direction, this direction, the vertical ones, okay, so let me put in perspective as a transformation. So if this is our Y, and this is our Z, this is our rotation X, right? So this force over here, right,